So, let us move to the last lecture of this week, which is the lecture number 20, which is AFM cum Electrochemistry Workstation. So far this week we have discussed about basic atomic force microscopy. We talked about all the different modes, how the AFM tip could be capitalized, contact mode, non-contact mode, intermittent mode. Then we talked about how you couple AFM with spectroscopic tools. Then we talked about how it is coupled with Raman spectrometer, how it is coupled with infrared spectrometer. Today we will talk about, in this lecture, which is lecture number 20, about how it is coupled with electrochemistry workstations, because this is another interesting part. So far we talked about, when we talk about the spectroscopic tools, prior to this we talked about the presence of different kind of chemical moieties. Presence of different kinds of chemical moieties. But in a dynamic surface, there are always changes which are happening. There may be events happening, there may be oxidation, there are reductions. In other words, there are electron transfer events which are continuously happening on the surface. And suppose we have to probe a surface like that, which is electrically active substrate, where there are movement of ions which are happening, electrons are shifting places. So, this kind of setup is used exclusively for that kind of study, where parallelly you can see the dynamic interaction of molecules, atoms on the surface of the sample. So far whatever we have talked about static presence of certain functional groups or wide range of functional groups, topography, elasticity, bending, flexibility, three-dimensional geometry. We haven't talked about electron transfer, right? Now we will be talking about electron transfer. That brings us to most advanced models, an integrated exchangeable 3-electrode electrochemical setup for AFM based scanning electrochemical microscopy. So, getting back to the basics, those of you have followed me in a bioelectrochemistry course prior to this, there are 3-electrode configuration used for any electrochemical setup. One is the working electrode, the other one is the reference electrode, third one is the counter electrode. Okay. So, reference electrode is basically almost like a universal reference, like hydrogen, platinum electrode, which basically gives you a reference value for everything. This is just like a pH. This is a reference value. Based on this, something will be acidic, something will be basic, just like that. There is a reference electrode. Then you have the working electrode, which is really the measuring electrode, and you have the counter electrode. Okay. Now, whatever measurements we make, we make between the working electrode and counter electrode, and we compare it with the reference electrode, or we can compare the reference electrode with counter electrode. Parallelly, we can compare between reference electrode and the working electrode, and then eventually we get the value, right. Now, assuming a situation where your reference electrode is a AFM tip itself. Now, your AFM tip, as I have already mentioned, it is moving on the surface, it is detecting, right. Now, say for example, the surface, it is also conducting. Say for example, it has the ability that it can conduct. So, now you are changing the nature of the tip to be a conducting tip, so that of course it should be able to sense what kind of movements which are happening out there at the surface. So, to look at it in the schematics out here, schematic representation of the classical set of AFM based ACCM with microscopic electrodes. A commercial AFM ACCM cantilever is connected to a potentiostat as one working electrode, while the sample is the second working electrode. The electrochemical cell is based on AgAgCl and platinum wire, which is basically your reference electrode as quasi-reference and counter electrodes respectively. The photograph shows a commercial ACCM cantilever as well as the electrochemical cell with reference and counter electrode. Left schematic shows the cantilever with the setup based on the commercial AFM ACCM cantilever screen printed electrode on its glass packaging. Here the working reference and the counter electrode are fully integrated into the ACCM cantilever chip. From 3 electrode experiment, no additional wiring in the fluid is required, hence a standard fluid cell is viable for measurement in the right bottom. So, this is one of the most compact model of where the tip is being integrated with printed electrodes. See, whatever you see out here, all these are kind of printed on the surface. Now, what really you figure out from this? This is a classic situation. Say for example, this is your substrate in gold nano mesh used for test sample in the AFM ACCM. Working principle feedback mode under bipotentiostatic control. Dashed line shows indicate electron transfer reaction on the electrode, while white arrows indicate diffusion of redox species. Okay. So here what you see, there is an electron transport phenomena which is happening, right. So here either you are gaining electron or you are losing electrons, right. On the other hand, on the insulator surface, no such phenomena can be really seen, right. So, dashed line indicate electron transfer reactions on the electrode, while white arrows indicate diffusion of redox species. They are moving out there. The schematic graph of the corresponding normalized tip current to positive to negative green feedback demonstrate the dependency of the sample distance. The dashed line mark the diffusion limits of the bulk current. So, what you see out here is that, say for example, on a surface, your sample has certain parts it is conducting, certain parts not conducting. As your tip is moving through, it could figure out where it is picking up the signature of oxidation, reduction, or where it is not seeing anything. So, you can spatially map a substrate of about its potential or electrical activity using a AFM tip. Otherwise, if you look at it, a normal electrochemical setup, if I look at a normal electrochemical setup, it will be something like this. Say for example, this is your working electrode WE, this is your counter electrode CE, and here is your reference electrode which is RE. And of course, in working electrode you have your compound and you measure it, but you have no idea about how this compound is really distributed. Now, say for example, this working electrode is no more like this. Now, this working electrode is something like this. and of course, you have this is the WE, this is the CE, and this is RE, and here is on the sample. Now, this tip is moving across and it is picking up where all you have the reaction sites are there, how it is all distributed. You get a very dynamic spatial picture of things which otherwise was not possible. And this is the power of when you are coupling two different kind of techniques out there, where you can see the electron transport phenomena which is happening. Now, if you take the parallel image of it, so far what we did, we try to image the whole substrate, right? Here you are, what you are seeing is imaging the whole surface. Now, if you look at this image, this is how it looks like. So, you see again the three-dimensional features are getting back, and you could say that these are the zones or these are the zones where you see certain features which otherwise were not present. So, that you can figure out which are the reaction sites where oxidation, reduction or electron transfer are happening. You can really locate all those spots far more easily versus when you are just doing a static electrochemical measurement as shown out here. Okay. Now, whenever you get a picture like this, if you remember, this is where we all started. I was telling you that there are multiple ways AFM could be useful. This is the image schematic of different kind of antibodies which could be used for detection of pathogen. But then behind this one picture, there is this whole story of, if I go back and take you back where we all started with this, I'll kind of give you a revision of what all we talked about. Let me go back by one, and that will, one second, as I'm almost finishing this particular week, let me take you back to that slide where we started this. So, this is the quartz crystal balance when we did, even before this, impedance analysis, right to this, sensitivity, theory of its piezoelectric crystal, here it is. So, it started out here, and I told you electrochemical sensors, optical sensors, right, and they go hand in hand. Then you have the nanosensors, and of course, mass will be coming soon. Here we talked about QCM earlier week. Now we are talking about Raman, IR, piezoelectricity, electrochemical, and you have the AFM signatures, and one second, yeah, you have the nanomaterials out here, and then next we'll go to the SPR likewise. So, if you look at it, whenever we and what we are detecting are these kind of things using these techniques. So, in order to understand all these things, now you realize why I need to spend for each one of them this much time, so that you understand that this is a very holistic approach. There is no simple way to gain insight into it unless you completely get a feel of it. So, if you recapitulate what all we did, so we started with the quartz crystal microbalance and piezoelectric resonator, and now you saw the use of piezoelectric resonator also came in the when we talked about the AFM, right. So, now coming back to this whole week, what we talked about, we started with the AFM as a sensing apparatus. So, these are the first, I asked you that you have to look for a repetition or a orderliness. These are the areas atomic topography, nanomechanics, electromechanics, nanoelectronics, nanospectroscopy, nanoelectrochemistry. Why AFM, we discussed about it. Then we talked about the basic forms of AFM, from surface profiling to all the way to coupling it with electrochemical setup and spectroscopic setup. Then we talked about the different kind of tip sample interactions, contact forces. These are the contact mode, non-contact mode, intermittent mode. Then we talk about the S norm, which is scattering, scanning, near field optical microscopy. Then we talked about infrared scattering, scanning, near field optical microscopy. Then we talked about SNOM, scanning near field optical microscopy. Then we talked about near field Raman imaging. We talked about tapping AFM IR mode, which is even much more powerful tool. Then we went on to talk about the contact resonance AFM. Then we talked about the basics of the Raman and the IR spectroscopy. There we talked about the polarizability in Raman spectra, the basis of the Raman spectra, and the dipole moment in the IR spectroscopic measurements. Then we talked about the Raman shift, and while talking about the Raman shift, we talked about the Rayleigh scattering and how we need to get rid of the Rayleigh scattering, suppress the Rayleigh scattering in order to get the Raman spectra, because Raman spectra get submerged because the Rayleigh scattering is much more higher. And we talked about Stokes and anti-Stokes values. Then the representation of the Raman spectra. From there we moved on to a comparison between IR and the Raman spectra. Then we talked about the comparison of homonuclear and heteronuclear distribution using Raman and IR spectroscopy. Then the complementary relationship between Raman and IR. And then we moved on to the applications of Raman all along in the pharmaceutical industries, food industries, as well as in the biological materials and in the biopolymers. Then we talked about coupling Raman using a multimodal platform for coupling Raman with imaging, where Raman, AFM and microscopic techniques could be used together. Then we talk about the selection of laser and how the choice of laser can ensure certain advantage and certain disadvantage, especially how to get rid of the fluorescence, challenges of removing fluorescence either using low energy laser or very narrow aperture or by using algorithms. And I discussed with you the challenges of using algorithms. Then we talked about how you clear up the whole spectra and get the corrected spectrum from Raman. From there we moved on to the lecture where we talked about how you can transform an electrochemical setup into a very powerful electrochemical setup integrated with AFM tip, so that you get dynamic movement of electrons on a surface. So that's where we are concluding this week, and in the next week we'll go further into deep with other different tools. As we are now finishing the 4th week with all these backgrounds so far, with spectroscopic techniques, with electrochemical techniques, with atomic force microscopy. From here we will discuss a little bit about interaction of materials and light, and then we will move on to the other more finer techniques which will help us to identify the chemical moieties of the pathogens. And again we will put more thrust on multimodal modeling and multimodal instrumentation and detection systems. And in that process we will keep revising what we have already studied till now, and we will take more and more case studies. So, with this I will conclude this week and thank you. So, let us meet next week with newer stories. Thanks.